Assalamu alaikum. So today we'll discuss the parent magnet AC machine modeling. Now simply, the parent magnet AC machine consists of stator and rotor. The stator is identical to the three-phase induction machine or the three-phase synchronous machine, in which it has three-phase stator winding, identical windings displaced by 120 degree from each other. So let's assume this is the start and the end terminals of phase A, and here the current is out and here the current is in. So this will be the AS dash and this will be the AS. So according to the right hand rule, this will be the direction of the MMF of the phase A. So this will be the AS X. Now 120 degree from the phase A, we have phase B. So let's assume those are the terminals of the phase B, and here the current is in and here the current is out. So this will be the BS, this will be the BS dash, and this will be the direction of the induced voltage for the phase B. The same thing for the phase C. So let's assume those are the start and the ends for the phase C. So this is the CS dash and this is the CS, and this will be the direction of the induced voltage of the phase C, and this is the BS. So simply here the stator, so here we can write the stator has three phase. Let's assume it's Y connected. Windings. Those windings are identical windings and displaced by 120 degree from each other. Now for the rotor, it's actually a magnet, so it's a parent magnet. So let's assume we have a two-pole, and let's assume that it's non-cylindrical rotor, and let's assume this is the north pole and this is the south pole, and we know that the d-ax is the ax of the field, so this will be the d-ax, which is the field ax, and let's say 90 degree ahead of that is the q ax, and this ax is rotating by omega r. So simply the angle from here to here is theta r, and we know that theta r can be written as the integration of omega r d tau plus theta r of 0, and theta r of 0 is the initial rotor position. Now this is actually a synchronous machine, so if we need to drive it, in general we need inverter, a voltage source inverter, in order to drive the machine. And to drive the machine we need theta r, we need the position of the rotor. Simply we have a lot of options to do that. The first one is using Hall effect sensors, let's say. The second one is to use encoder. Those are devices that we can use in order to measure the rotor angle. Of course, we have also a method to estimate the rotor angle. In this case, this will be a sensorless method. This later on we'll discuss. So simply, now if we plot here the electrical circuit for the stator, it's actually by assumption we are assuming Y connected. So let's assume that we have the following three-phase winding. And let's assume this is the phase A, so this will be IAS, and this will be plus minus VAS. This will be the RS, the stator resistance. This will be the NS, the equivalent number of the turns of the stator windings. And those are identical for all the phases because we are studying symmetrical or balanced three-phase machine. And let's assume that this is the IBS. So this will be the VBS. And the same fashion, this is RS and S. And this is the CS terminal, so ICS. And this will be the VCS. And this is the R, and this is the N. Now for the rotor, I will not plot anything because simply the rotor has no physical windings. So simply there is no circuit in the rotor, and this will indicate that in terms of the efficiency, this motor is high efficient motor because there is no copper losses on the rotor circuit. The rotor is a magnet, there is no winding on that. So if we need to write the voltage equation, we need only to write the voltage equation for the stator. So this is the stator circuit. So simply here the voltage equation in machine variable in the ABC reference frame. And it's actually the Ohm law plus the Faraday law of induction. So this is the VABCS equal to RS IABCS plus d by dt of lambda ABCS. And R here is diagonal matrix. So simply we can write here R of S is a diagonal matrix. So now we need to find the flux linkage for the stator. Now simply recall that the flux linkage for the stator consists of two parts. The first one due to the current in the stator, and the second one due to the current in the rotor. But simply we don't have a current in the rotor, but simply we have a magnet. So here we can write the flux linkage. So lambda ABCS will equal lambda ABCS due to the stator plus lambda ABCS due to the rotor. So simply lambda ABCS will equal. Now the flux linkage due to the stator simply can be written as LS IABCS. Of course, we are assuming a linear magnetic circuit plus now the flux lambda ABCS due to the rotor. This one is constant, and this one is equal lambda m. And let's assume it's lambda m, and this lambda m in the direction of the dx. So simply all the flux of the rotor is pointed toward the dx. So this one is the d. So simply the flux of the rotor is here, lambda. So if this is the AS and let's assume this is the QS and this one is theta R. So this angle is actually the pi over 2 minus theta R. So this means that lambda m, this lambda m will equal to lambda m as a magnitude multiplied by the projection of the rotor flux into the AS, which is the lambda m cosine theta r minus pi over 2, which is the sine theta r. So this will be sine theta r, and the projection of lambda m to the BS. So the angle here is 120 degree plus pi over 2 minus theta r, which will equal sine theta r minus 2 pi over 3, and the projection through the CS will equal sine theta r plus 2 pi over 3. Now this one is magnitude and this one is vector. So let's do like this. Now here the self-inductance actually is the same as the salient pole synchronous machine. Now LS is same as salient pole synchronous machine. So if you missed that, you simply can recall our lecture in the synchronous machine, the modeling of the synchronous machine in the ABC reference frame, and you can find, let's say, step-by-step method in order to calculate the self-inductance of the stator, which is here also is applicable. Now, the magnitude of lambda m, which is the flux due to the parent magnet, is constant because simply this flux is produced by a magnet. So lambda m is the amplitude of the flux linkage established or generated by the permanent magnet. And as this one as viewed from the stator winding. So simply this means that lambda m is constant. Of course, if we neglecting the aging effect, which means that d by dt of lambda m is equal to 0. So now we have the voltage equation. So simply here we have the voltage equation, and if we need to finish the model, we need an expression for the electromechanical torque, and we need the swing equation. So we know that the electromechanical torque can be found by differentiating the co-energy with respect to theta r. So simply here we can write the electromagnetic torque in machine variable in the ABC reference frame. So TE will equal partial omega C by partial theta r mechanical, and this will equal P over 2 partial omega C by partial theta r. So we need to calculate omega C, and because we have a linear magnetic circuit, we know that omega C is equal to omega F. So simply we can write omega F, which will equal to omega C. So omega F is equal 1 over 2 I A B C S transpose L S I A B C S plus I A B C S transpose multiplied by lambda m as a vector, and simply a plus, let's say, omega p m, and this one is actually energy in coupling field due to the parent magnet, and this one is constant. So this actually is the energy in coupling field due to the parent magnet, and this one is constant. So because we are assuming a linear magnetic circuit, so simply this means that omega C is equal to omega F. So now we have omega F here. So simply this means that we have omega C. So now we can calculate TE, which will equal P over 2. Now we will differentiate 1 over 2 I A B C S transpose partial L S by partial theta R I A B C S plus I A B C S transpose partial lambda m by partial theta r. Now, if we do the math, of course we don't need to differentiate this one because this one is constant, but we need to differentiate this one with respect to theta r because lambda m is a function of theta r. So simply lambda m is a function of theta r. So if we do the math and collect the terms, TE will equal to P over 2. Here we can write LMD minus LMQ over 3. Open the bracket here. Another bracket. This would be IAS square minus 1 over 2 IBS square minus 1 over 2 ICS square minus IAS IBS minus IAS ICS plus 2 IBS ICS sine 2 theta r plus square root of 3 over 2 multiplied by IBS square minus ICS square minus 2 IAS IBS plus 2 IAS ICS all multiplied by cosine 2 theta r plus lambda m multiplied by IAS minus 1 over 2 IBS minus 1 over 2 ICS all multiplied by cosine theta r plus square root of 3 over 2 IBS minus ICS sine theta r. Now simply, if you notice that the torque expression in machine variable is very complicated, simply we cannot figure out which term we should control in order to control the torque, and in terms of the control this expression will be useless. And simply here, if we need to let's say finish the definition, we should give the definition for LMD and LMQ, although we already know from the synchronous machine. So LMQ is equal 3 over 2 LA plus LB, and LMD will equal 3 over 2 LA minus LB. So keep in mind that this torque simply is very complicated. You cannot figure out which term you should control in order to control the torque. And in terms of the control theory, or from control point of view, this expression will be useless. But simply for the modeling, this one is accurate. And if we need to do the model in the ABC reference frame, simply we need an expression for the torque. Finally, if I need to finish the mathematical model of the parent magnet AC machine or synchronous machine in the ABC reference frame, we need to find the relation between the torque and the speed, which is the swing equation. So simply here we can write that the torque and the speed are related by the swing equation, which equals J. Here I will write it in terms of the electrical speed, partial omega r by partial t, or d omega r by dt, plus b m 2 over p omega r must equal the summation of the torque, which is Te minus TL. Now we have expression for Te, and TL, this one is the load torque. And simply this is the moment of inertia, and this is the damping coefficient or the viscous friction. So simply here, this one is the damping coefficient, or sometimes we can call it the viscous friction. Now, simply in the same fashion of the three-phase synchronous machine and the induction machine, we can use the reference frame theory in order to simplify the mathematical model, and in order to, let's say, find a simple and more insight expression for the torque and the voltage equation, and for that we can use the reference frame. So simply here, which reference frame we'll use? We'll use the rotor reference frame, because the rotor already in the QD reference frame. So here automatically we can write the voltage equation in rotor reference frame. Why the rotor reference frame? Simply because this machine is synchronous machine, and the inductance matrix will be constant if the adopted reference frame is the rotor rotating reference frame. So in the same fashion, we will find VQ D0 SR, which will equal RS I QD0 SR plus omega R lambda DQ SR plus d by dt of lambda QD0 SR. Now, where lambda dq SR transpose is equal to lambda dsr minus lambda qsr and 0. So the same thing here. Now we have an expression for the voltage equation in the QD reference frame, where we have a meaning for each term. For example, this one is the drop voltage across the resistance, Ohm law, and here this one is the induced voltage due to rotation, and this term is the induced voltage due to the static coupling. And in the rotor-oriented reference frame, the flux linkage lambda QD0SR will equal to, the inductance matrix now will be a constant, so this will be the LS plus LMQ 0 and 0 multiplied by the current, so this will be the IQSR IDSR I0SR, and here we have 0 LS plus LMD 0, and here we have only the leakage inductance. Now this is not all expression for the flux linkage, because simply we have also the rotor is pointing in the direction of the D, so this will be plus the vector, which is the 0 lambda mr 0. Now if we recall, all of the rotor flux is pointing toward the D axis, and the axis is rotating by omega r. So simply now we can expand the voltage equation. So if we write the voltage equation in expand form, so VQSR will equal to, let's change the color. So VQSR will equal to RS IQSR plus omega r lambda d SR plus d by dt of lambda q SR. And here are simply to indicate that the adopted reference is the rotor reference frame. So this to indicate the rotor reference frame. Now, what about the VDS? So VDSR will equal RS IDSR minus omega r lambda q SR plus d by dt of lambda d SR, and finally V0 SR will equal RS I0 SR plus d by dt of lambda 0 SR. Now we can write lambda QS, lambda DS, and lambda 0S also. So the flux linkage, so where lambda QSR will equal to LS plus MQ IQ SR. So this can be written as LQ IQ SR. So simply this actually is LQ, and lambda DSR will equal to LD IDSR plus lambda. Here the same, LD will equal to LS plus LMD. And finally, lambda 0S R will equal to LLS I0S. Now, if we substitute the flux linkage in the voltage equation and we collect the terms for the current, the voltage equation can be written as so VQSR will equal to RS RS plus d by dt LQ IQ SR plus omega R LD IDSR plus omega R lambda m R. And simply d by dt is the differentiation operator, so it will differentiate the current, let's say. Now VDSR will equal to RS plus d by dt of LD IDSR minus omega R LQ IQ SR, and finally V0S will equal RS plus d by dt of LLS I0S. And remember, the inductance are constant. So simply the derivative operator only will differentiate the current. So simply also we can find an expression for the torque from the voltage equation in the QD reference frame by calculating the power. So let's calculate the input power in the QD reference frame. So the input power in the QD 0 reference frame. Now, if you remember, Pn must equal to 3/2, this one due to the transformation, and from the transformation we found that it will equal VQS RIDSR plus VDSR IDSR plus 2V0S I0S. This one here is the Q. So this VQSR IQSR plus VDSR IDSR plus 2V0S I0S. Now, because we are discussing symmetrical, this term is equal to 0. I will not carry it with me, or simply because there's no speed voltage in the 0 sequence, so I will not carry it with me. So simply Pn will equal to 3/2, and this one due to the transformation in order to make the power in the QD reference frame equal the power in the ABC reference frame. Now if we substitute VQS VDS here and multiply, collect the terms, so this will equal to RS multiply by IQSR square plus IDSR square. If you need to carry the 0 sequence, you will get here plus 2I0S square plus lambda dsr iq sr minus lambda qsr I dsr multiplied by omega r plus iq sr d by dt of lambda q s r plus id sr d by dt of lambda d sr plus 2 I 0s d by dt of lambda 0s Now, let's see. Simply, this term here is the ohmic power losses in the stator. And this term here is the change of the stored energy. So the only term that is converted to the out power is this term, which is the term that containing omega r. So this term is the converted power. So simply, from here we can calculate TE, which will equal the power converted over omega m. So this will equal to omega m omega rm. This will equal P over 2 P converted over omega r. Now simply P converted, we have it. So if we substitute, we will get TE is equal to 3 over 2 P over 2 lambda dsr iq sr minus lambda q sr I dsr. Now we can substitute instead of lambda ds, which is the L d I dsr plus lm, and we can substitute instead of lambda qr with its expression, which is the lq iq sr. Now if we do that, we'll get TE is equal to 3 over 2 P over 2 lambda iq sr plus LD minus LQ IQS IDS R. Let's rewrite it here. So LD minus LQ IQSR IDSR. Yeah, that's perfect. So simply, this torque actually is due to the interaction between the perth magnet and the stator, and this torque is the reluctance torque. So if the machine is cylindrical, which means that LD is equal to LQ, only we have this term here. So for cylindrical rotor, TE will equal to 3 over 2 P over 2 lambda IQSR, and simply this term is constant. So simply this means that TE is proportional with IQSR. And this one for the cylindrical rotor when the gap is uniform. So now we have the voltage equation in the QD reference frame, and we have an expression for the torque in the QD reference frame, which means that we also have the model of the parent magnet AC machine in the QD reference frame. So next time I will discuss with you how to control or vector control of the parent magnet AC machine. Until that,